Hello, my name is Mike Kolbeck, and today I'll be walking you through my implementation of the Neural Networks and Deep Learning Final Project, the Kaggle competition where we use the weather data to predict a temperature at a given time. Today what I'm going to be doing is walking you through how I analyzed and prepared the data to kind of figure out what I wanted to do, the model that I chose and how I trained it, and then kind of the journey along the way of tweaking the hyperparameters and kind of getting everything just the way that I did. So to kind of start off, I first downloaded the data set from the class website as a CSV file and kind of just sort of took a look at the variables that we were working with. This didn't really tell me a whole lot to start off with, so I kind of did some graphs to kind of figure out whether there were trends or not to find in the weather. We can kind of see by just looking at different randomly chosen days that there do seem to be kind of like peaks and valleys and a lot of these upper metrics here, as you know, it gets warmer and that influences other things. And then some of these other ones down here kind of have this kind of like more jagged peaks and valleys throughout the day. So clearly a pattern there to find, but maybe not super clear to the human eye what that means. I also kind of graphed out some longer term things using kind of the scikit-learn plot functions. Found out that within a month there's these kind of up and downs that would suggest on a day-to-day basis that some kind of cycle is happening. And then by taking a look at like a year, which is kind of this up and down or these little up and down patterns here, that there were clear seasonal cycles. So there was clearly a number of patterns to find, which suggests that machine learning algorithms would have something to grab onto, but didn't really tell a whole lot about the data and what we'd have to do to clean it. So I kind of printed it out here, and this kind of tells us that it needed a little bit of work. The date time we could just throw away because that's not really going to really be predictive of anything. But everything else is floating point numbers, which is great. But they ranged all over the place. So the temperature ranged from like -10 to positive 40. Whatever RHO is ranged up to the thousands. So there was some normalization that would have to happen to keep some of these numbers from overpowering others and kind of throwing off the accuracy of our model. So what I did there was, given that all these were floating point numbers and of various different scales, I kind of reshaped everything into a list of lists. I thought that maybe it'd be easiest to do this data crunching in strictly using pandas, but it turns out that the data frames were actually slower to manipulate than just a list of lists for some reason. Once I had it into a shape where I had kind of everything sort of going horizontally, I used these min-max scalar objects from a library that we imported and range them from 0 to 1 just to kind of extract out those negative quantities, which ended up actually causing a lot of trouble in my model when I try to go from -1 to 1. We kind of hold on to these scalars because later we'll use it to unpack our predicted y values and kind of get back to the temperature range we'd actually expect with our output, because our output's just going to be from 0 to positive 1. Once I did that, I split everything into data frames and kind of got our x and y training and test data, which we use to train the model. So at this point in the process, everything is ready to go, properly scaled, cleaned up, and we can kind of move on to the actual model that I trained here. So I had to move it into this sort of three-dimensional array of kind of all of the n number of rows, but each row being 24 sets of 14-hour arrays. So this is 1 hour array once it's been normalized, and then there would be 24 of these kind of going across, and then each one of those would effectively be one of these rows that we get plugged into the data. So the model I started with was a very simple LSTM network. Use the sequential kind of base class, build a 32-cell LSTM, did return sequences but not state, and I used the kind of input shape that was required. 14 metrics across 24 hours trying to find the y value that happens right after that. Use these compile functions, and I got a Kaggle score out of this of 0.47180 or an MAE. So this was pretty good, and I thought that as a starting point, this was a great first attempt, and that I would find something else that would do better. Taking a look at my rough draft over here of kind of the different models that I tried something in the ballpark of 20 other models, and not a single one of them actually beat this Kaggle score. So this was really surprising to me, as this is a very simple neural network, but I tried dropout, I tried stacked layers, I tried recurrent neural networks, I tried different LSTMs, I tried bidirectionality, returning the state, really a lot of other parameters that we could use here, and I've got kind of a breakdown here. So running it for more epochs, recurrent dropout, gated recurrent nets, convolutional LSTMs, even a Gator curl network paired with convolutional layers. What I found was just really nothing exceeded this very simple 32-cell single LSTM layer. I also looked at RMSE as kind of just like a secondary error metric, just to get an idea of what was performing, how well. That one, it only came in second, and this 32 cell stacked, three stacked 32 cell stateless neural network also did relatively well. But really, it was just this one layer instead of a 3 layer that kind of knocked it out of the park in terms of the Kaggle score. Just kind of for giggles, I also put kind of my zaniest other network here, this kind of convolutional layer leading into a GRU. Didn't perform super well, but kind of wanted to just demonstrate that there was some variety in the models that I chose. But in the end, this actually did quite well. I plotted out, so we got the predicted Y values here, the inverted Y hat, and this inverted hat came from reusing these scaling objects that we had before, and inverse transforming the data that got spat out, the 0 to 1 scale data from the LSTM. And by kind of plotting these together on these graphs, you can see these little itty bitty blue sort of notches at the end. That's an intersposed prediction line and an actual line. So the predictions are very close, and just looking at a single day, it also mirrored very closely what actually happened. So definitely not perfect, but I think the single LSTM, even just a single layer of like LSTM cells, is a very powerful predictive tool when it comes to detecting patterns in time series data. So actually, then to submit it, all I did was I would just kind of write to an out file, CSV, and kind of figure out the latest one in there and add on another number, and I would ship that off to Kaggle. So that's kind of the model that I chose to submit here, and kind of why I did. It's just it just scored the most. It was not a particularly deep network. It didn't really have a lot going on technically, but for some reason it just kind of knocked it out of the park score-wise. So that's what I went with here. I'd highly encourage you to take a look at this graph here to kind of that sort of compares all the different things that I tried, just to get an idea of sort of what was out there, what maybe did a little bit worse, what did a lot worse. And just for reference, I'll also upload this rough draft that just kind of contains the implementations of all the other networks that I tried. Hope this helps, and thank you for watching. Take care.